Okay, we'll go ahead and get started. Can everyone on Zoom hear me and see the screen okay?
Yes.
Okay, great, thank you. So what I'd like to do today is I'd like to go over the quiz that we had and talk about that a little bit. Then we'll finish up chapter 2. And then if we have some time remaining, we'll start kind of reviewing for the exam. The other thing I wanted to say is we were scheduled to have the first exam on Monday. We're going to push that back to Wednesday. And on Monday, we'll do some prep work for the exam. So the quiz. Basically with the quiz, you fell into one of two buckets. Either you did really well or you did poorly. It's pretty unusual in looking at the grades. So in the class, 50% of the people got an A or a B. 40% of the people got a D or an F, and then 10% got a C. That's pretty unusual. Usually you have more people in the middle with C's and then a little bit on the D and F side and a little bit on the A and D side. So, so to be honest, I don't really know what that means. It was surprising to me to see that kind of distribution. You would call that a bimodal distribution. You have the high mode and the low one. But what we're going to do though is, I think it's really important that these first couple of chapters that people get that stuff. Because if you don't get it, it's going to make the rest of the semester and the next semester difficult. So we're going to take a little bit of a step back here and we're going to review the quiz so people can see what the correct answers were and kind of the thought process you would have used to get to those answers. And then we'll finish up chapter 2. After finishing chapter 2, I would ask you to go and take a look at those homework problems and work on those between now and Monday. And then on Monday, what we'll do is we'll kind of go back through chapter 1 and chapter 2 and kind of review stuff a little bit. And I want to just go back and highlight the parts that I think are particularly important. So in other words, if you're going to focus your studying on something, I would focus it on these things that we go through in the review, because those will be important for the exam next Wednesday, but it'll also be important just as we carry through the rest of the semester. Okay, any questions about any of that? Okay, the other thing I'll just say is, if you were in the bucket that got an A or a B, I would say good job, congratulations, good work, keep it up. All right, it's a long semester, there's a lot of points, we got 4 more quizzes, we've got 5 exams, we've got a final, so there's a lot of points still left out there. By the same token, if you were one of the people who didn't perform as well as you would have hoped on the quiz, don't give up. I'll say the same thing to you. There's a lot of points left. There's a lot of quizzes to take, a lot of exams to take, a lot of opportunity to make up. And remember also, you get to drop the low quiz and you get to drop a low exam. So one bad quiz or one bad exam doesn't ruin your grade. 2, 3, 4 of those will impact your grade, but one will not. So let's take a look at the quiz. So the 2 sections had similar quizzes, but for the most part, they were different. There was one question that was the same on each quiz. So this is the quiz that section 1 received. The first question, the law of constant composition applies to Solutions, heterogeneous mixtures, compounds, homogeneous mixtures, solids. The correct answer is C, compounds. Remember, that law of constant composition is where we say that if it's water, it's always H2O, that doesn't change. And so that's what we apply to compounds, so that we know that a particular compound always has the same composition. Any questions about that one? Okay, number 2, which one of the following element has the correct element name and symbol? So we have sodium, tin, iron, neon, bromine. Iron, C, Fe, was the correct answer there. The others are incorrect. What's sodium? Does anyone know what sodium is? Na, right. How about tin? Anyone remember tin? Sn, correct. Neon, how about neon? Ne, right. And bromine? Br. So I know I had a lot of comments about timing on the exam. Well, this is the type of question that we have on the exam, which is the exact reason why we have the timing. Because you can look stuff up and that, I'm not certain if anyone in the class missed this question. And I assume that's because even if you didn't know it, you could just look it up really easily, real quickly. Well, that's where the time factor comes in, is that I don't want you guys to get into the habit of just looking everything up, because that's not the purpose of the class. The purpose of the class is that you're learning these things, you're learning the basics in this class in general chemistry that kind of take you forward as you take other chemistry classes, other science classes. And so really these element symbols and associated names are something that you really want to get to the point of where you don't even think about it. You just know it immediately. The next question, let me scroll up here a little bit. In the following list, which is not a chemical reaction example? Hold on here. So if we say something has a chemical reaction, what are we really saying? We're saying that there's not just a physical change. There might be, but we're saying it's not just a physical change, but the material itself is having a chemical change. So we go back to question number 1, where we talked about constant composition. Well, in 3 here, we're saying if there's a chemical reaction, that composition of the compound is changing. So that's the difference there. That's the difference. The physical change can be something where we gave water as the example, where it starts as a solid, then you can melt it, it becomes a liquid, and then the liquid you could heat up and it become a vapor. So in those cases, you have a physical change of the water, but you don't have a chemical change. So when we look at our choices here, we see dissolution of a penny in nitric acid. We see condensation of water vapor. We see burning a candle, formation of polyethylene from ethylene, rusting of iron. So which one of those is not a reaction? Well, the first one, if you have a penny and you're dissolving it in nitric acid, you're most likely undergoing a chemical reaction, because metals don't typically just dissolve. The condensation of water, we talked about that. Water was one of our big examples of moving around in different physical forms, but the water itself doesn't change. So there's no chemical reaction there. So the answer is B. Burning of a candle, if you think about that, what happens when you burn a candle? Obviously you get a flame and you get light, but that candle goes away, right? Physically, a candle will go away when you burn it. So that tells me that I'm changing whatever that candle is made of into something else, because it's volatilizing away. So that's a chemical reaction. And then formation of polyethylene from ethylene. Even if you don't know what ethylene or polyethylene are, and at this point you may not, it's talking about a change where you're taking one compound, ethylene, and creating polyethylene. And remember, our definition of a chemical change is we're making a change of that material, a chemical change of it, not just changing physical state. So once again, that would be a chemical reaction. And then rusting of iron. So if you've ever seen things rust, you see the formation of that kind of brownish, orangish color on the metal. Well, that's, in that case, that's an oxidation reaction, but you may or may not know that part, but you definitely know that you're seeing a change, some type of chemical change going on. All right, number 4, of the following, which is an extensive property? So we talked about intensive and extensive properties. What's the difference? If it's intensive, it's independent of how much stuff we have, right? If it's extensive, then it is dependent upon how much stuff we have. So when we go through this list and we have density, for instance, what was the definition of density? That was the amount of weight per volume. So that's not going to change. Your weight per volume is going to be constant whether you have a little bit or a lot. Volume. Does the volume change by how much you have? Yes, it does. That's kind of the definition of volume, is how much stuff do you have. If I say I have a liter of soda versus 500 mils of soda, that's telling me I have more soda in the liter than I have in the 500 mils. So that is an extensive property because it's based on how much stuff I have. Boiling point. Well, if we're boiling water, it doesn't matter if we're boiling a little pot or a big pot, the temperature at which it boils is going to be the same. Same with freezing point. Water freezes at a certain temperature, whether you have a little or a lot. So once again, those are intensive things because it depends on how much you have. And then finally, temperature, that's an intensive one as well. So the only extensive one is B, which is volume. Now, number 5, everyone's favorite problem. So this one is actually very similar to what we did in the first actual lab, where we used in the lab, if you remember what you did in the lab, and I think everyone's had that first lab now, you did in that lab, you had an amount of water that you knew, you added some metal to it, saw that difference in volume, and then used that to calculate some things about the metal. So here, we're told that we have a metal sample and we place it in a flask. Then we add water and we record that volume. They give us the mass of the water, flask, and metal. So in other words, they had that flask with the metal and water in it, and they weighed that whole thing. And that's the 268.5 gram value. They give us the weight of the mass, of the flask. So in other words, before they added anything in, we weighed that flask, and that's the 139.3. And then, of course, we had the weight of the metal up front. That's the 4.369 grams. So we have that total value, that 268.5. We have the weight of the flask, the 139.3, and we have the weight of the metal. If we subtract the weight of the flask and the weight of the metal from that total weight, then we get the weight of the water. So now we know the weight of the water. And when we think about this, we want a density, right? And let me ask you this question on this. When we're talking density, we can express it in several different ways. One is grams per mil, but the other is grams per centimeter cubed or grams per cc. Does everyone understand that cm cubed and mil means the same thing. Because if you didn't remember that, that was one of the conversion things we talked about. If you didn't remember that, then it might have confused you with that CMQ. But in setting up this problem, because we knew we had to get to density, you needed to get to grams per mil in your units. So we're going to do this stuff up front here is to get things lined up for that, okay? So now they tell us that the density of water is 1 gram per mil. So what that means is that 124.8 grams of water that we found from that initial subtraction of those weights, really, if we do the conversion, there's really no math there, but it tells us that 124 grams of water is the same as 124.8 mils of water. So now we have a mil value for water. Up in the problem, they told us what a mil value was for water plus metal. We were told water plus metal equals 126.4 mils. So we know what the milliliters of the water plus metal are. We know what the milliliters of the water are. If we subtract those, that gives us the volume that's attributed to that metal. So if we do 126.4 minus 124.8, we get 1.6 mils is the volume of the metal. So we were given the weight, 4.369 grams for metal, and now we've calculated out what the volume of the metal is. That's 1.6 mils. So if we do that ratio, because we want density, so we want weight divided by volume, we now have 4.369 divided by 1.6, and taking into account our significant figures, we get 2.7 grams per mil. And that was the answer, is D. So you had to do a little bit of a series of things to figure out there. But the key really was, we knew we wanted to get a density. And we knew the density was grams per mil. So then it was looking at the information we had to try and figure out, how do we get grams? Well, that was the easy part, because they told us right up front how many grams of metal there was. So the tricky part really was getting that volume of the metal. And that's where we had to take that information that they gave us about those initial weights, so the weights of the flask, the weights of all the stuff together, the weight of the metal, all that, use that to figure out how many grams of water were there. We were given the density of 1 for the density of water, use that to convert it to mils, and then take that total mil value with the water mil value and use that information to get how many of those mils were really attributed to the metal. And once we got those things set up, then we could do our ratio, our grams per mil ratio to get density. So the quiz and the answers are posted on Canvas. So if you want to look at this later again, you can. But does anyone have any questions about this before I go on?
Is a question like that can be on the test?
Pardon?
Is a question like this can be on the exam?
It could be. I mean, one of the big things in chapter 1 in terms of calculations are calculations centered around density. And so, you know, I think there's another one, I forget which is in which quiz, but I think there's another one in here that's a pretty straightforward density calculation. This is just a little bit more challenging. And to be honest, this is the kind of thing you'd be more likely to do. And we did something similar to this in the lab, of where you see how density and that relationship, that mass to volume relationship, can be used to figure some stuff out like this. So if you got this right, congratulations, good job. If you didn't, take a look at it. And what I would ask you is, to me, it's great if you got it right, but what's more important is if you start thinking about how you can use density and how you can set up the problems, okay? That's really what you're trying to strive for. This goes back to some of the dimensional analysis stuff I talked about before, of how important that is. And it really gets to where, you know, if you see a problem like this where there's a lot of numbers thrown at you, it's easy to get confused. It's easy to get kind of, oh my gosh, what am I going to do? I think that's where what you want to do is just kind of focus on looking at the units, looking at the information they gave you, just kind of piecing piece by piece the information they give you to build it up till you get to the end. Okay, so this was easily the most difficult problem on the exam, on the quiz. Okay, in this one, which item would be considered the most dense? Basically, the way I approach the problem is, for each of these, I just convert it to grams per mil. Most dense means the highest density number. So kind of similar to the last one where we talked about density. Here we wanted to get them all in the same density units. And for me, it's easiest to work in grams per mil and do that conversion. So to do something like this, and the answer is A, it's the piece of wood at 2.5 liter volume and mass of 12.5 kilograms. To do this problem, what you would have to have remembered was the table that we went over that talked about what these conversions are. So, for instance, 2.5 liters. How many mils are in a liter? How many milliliters are in a liter? Does anyone remember that? 1,000, right. And then how many grams are in a kilogram? 1,000. So that's where for each of these, see the next one is just grams per mil, so there's no conversion there. The next one, is that milligrams? Yeah, milligrams. So how many milligrams in a gram? So there's 1,000 grams equal a kilogram. How many milligrams equal a gram? Anyone know that one?
1,000.
1,000. And then kind of on down the line, nanograms. Does anyone remember what nanogram is? Nano is 9, 10 to the minus 9 grams. The others are grams and mil. But that's a problem where if you remembered those conversions off the top of your head, it's a pretty straightforward calculation. It wouldn't take you too long to go through that. If you're sitting there going, yikes, I don't remember what a milligram is or a nanogram is, you're probably going to struggle with that problem. So it goes back to some of those tables we talked about, learning those conversion factors. Okay, the next one, which calculation shows the temperature conversion of Kelvin and degrees C? And that's the first one. Kelvin is degrees C plus 273.15. I think this is another one that I think everyone in the class got correct. I don't think anyone got that one wrong. Number 8 is another one of these of learning the units. So for me, what I did when I look at this is I convert everything to grams once again. So we talked about this a little bit. Kilogram is 1,000 grams. Milligram, 10 to the minus 3. Picogram, femtogram. Pico's 12, femto's minus 15. Nanogram, 10 to the minus 9. So you have to remember those conversions and then move the decimal around a little bit with your calculator. Okay, 9, precision refers to how close a measured number is to other measured numbers, how close to the true value, how close to a calculated value, how close to 0, how close to infinity. Remember, precision is just how close is the number to the other data points that you got. So if you did 3 measurements, how close those measurements would be to each other is precision. Accuracy is how close you are to the true value. If you remember, we had the bullseye definition where all the arrows kind of hitting on top of each other. That was precision. Accuracy was when they hit in the center, in the bullseye, in the target. Okay, the next one is significant figure question. Round 0.007222, the three significant figures. So the first thing we all should hopefully know is those zeros to the left are not significant. So then it becomes 0.00722. The three significant figures that we would have are the 7, the 2, and the 2. It doesn't round up to 3 because it's below 5. So there's no rounding up that last one to 3. Any questions about that one? Okay, kilogram to milligrams, another one of these conversion type questions. We've talked about this a bit already. Kilogram is 1,000 grams, milligram is 10 to the minus 3 grams. So if you do the conversion, it's 10 to the 6th is the difference, which is D 1 million. Common theme here on a lot of these, you may have noticed, is if you had a good feel for those conversion factors and those tables, you would know these. If you didn't know those real well, you're going to struggle a little bit. Okay, density. This is a straightforward density calculation. They give us the volume, they give us the mass. We know density is mass divided by volume. So the key here is to do the calculation. Hopefully we did get the right number of significant figures. So we have 32.4 grams divided by 1.68 centimeter cubed or mils, however you prefer to express it. And then the answer is 19.3 grams per mil or grams per centimeter cubed. The next one. What is the correct answer with the right number of significant figures? So we have 6.3 times 3.25. So when we multiply, what determines the number of significant figures when we multiply two numbers? Anyone know that?
The number with the least amount of significant figures?
Right, the number with the least amount of significant figures. So in this case, we have 6.3, that's two significant figures. And we have 3.25. That's three significant figures. So we'll do our math, but then we're only going to have two significant figures in our answer because 6.3 is the driver in terms of significant figures here. In A, which is our answer, we have 20 with a decimal after it. If we didn't have that decimal after it, how many significant figures would that have? Right, just one. So that's why the decimal is there. So I think 20.475, if I recall, B is what the actual answer is. So once again, because that 4 is less than 5, we don't do any rounding to make it 21 like the answer is in E. So two significant figures, no rounding up because of what the non-significant figures are, and that gets us to 20 point as the answer. Okay, another density type question. So once again, I think this is the third density type thing. So, you were asking before, will there be any things like this on the exam? Well, we've had 3 density type calculations on the quiz. I think if you were gonna take a guess, would there be any density type calculations on the exam? The answer would be yes. So here, basically what we're trying to do is calculate out a volume based on the mass and the density that we're given. So if we line up our units correctly, we know we have 9.83 grams is the mass of the sphere. And then they tell us the density is 13.6 grams per centimeter cubed. In order to get those grams to cancel, we need to have the 13.6 grams in the denominator, because then the grams on the sphere number, the 9.83, will cancel with the grams on the density value and leave us with a centimeter cubed or mil unit, so a volume unit, which is what we're looking for. We do that math, we get 0.723, which in this example is A. Then finally, the tentative model that described the underlying case of physical behavior beyond its observation is called law, theory, hypothesis, experiment, test. So the answer is theory. Why isn't it hypothesis? Why is it theory instead of hypothesis? Well, the reason is they talk about beyond the observations. Remember when we talked about having hypothesis, that's just, we've had some observations, we've seen some things, and we're kind of taking a guess at what's going on. But the hypothesis doesn't have any follow-up data or anything like that. So when we get to theory, we start to have some data beyond just those initial observations. And that's why this is a theory and not a hypothesis. Okay, so that's the quiz. Any questions on any of those problems? As I said, it is posted. If you want to take a look at it later and just review it, that's fine. Okay, let's go on to chapter 2 then. Okay, so when we left off last week, we were talking about chemical nomenclature. So I'm going to pick up there and kind of go through this a little bit. The thing to remember about the nomenclature.
Professor, ours are still on the quiz.
Okay, thanks. What are you seeing now? Are you
Chemical nomenclature.
Okay, so you're seeing the slides, good. Thank you. So for chapter 2, and especially the nomenclature stuff, it's similar to some of the stuff I talked about in chapter 1, in that a lot of this is, you got to memorize it. There's no way around it. And so when we go through some of these rules on nomenclature, I'll go through them with you, but then I would suggest you go back, spend some time trying to memorize it, work some of the example problems to get used to it, and we'll go from there. So nomenclature, chemical nomenclature is just the term that we use for how compounds are named. We're going to talk about a few types of compounds here in this chapter. We're going to talk about ionic compounds and how those are named. We'll talk about acids. We'll talk about some binary molecular compounds. And we'll do a couple of the more simple organic compounds. So organic chemistry kind of has their own system of naming compounds. We'll talk about alkanes and alcohols to give you a taste for how that's done. If later on you take organic chemistry, you'll get a lot of this and you'll spend a lot of time learning how to name those compounds. When we talk about the inorganic compounds, we talk about the cation and the anion. Does everyone remember what the cation is? That's the positively charged part. And then the anion is the negatively charged part. And when you write them, typically the cation's on the left-hand side and the anion's on the right-hand side. So when we write, the cation can have oftentimes more than one possible charge. If it does, then we write that charge in Roman numerals in parentheses. And as time goes on, you get a feel for which ones have multiple charge potential. If it's a polyatomic cation, it will end in IUM. So ammonium is a good example of that. If the anion is an element, you change its ending to "ide." If it's a polyatomic ion, you simply write the name of the polyatomic ion. So an example of the element would be sodium chloride, so NaCl. So it's just a sodium with a chlorine, so you say chloride. A polyatomic ion would be, say, maybe sodium acetate. So you have the acetate ion, and it's acetate, so you just say acetate. So when you start having multiple oxygens in an ion, then those are called oxyanions. And so when you have the same element with different amounts of oxygen to it, then the one with the fewer oxygens begins with "ite," and the one that begins with more oxygens ends in "ate." So for instance, here we have with nitrogen and 2 oxygens, and then nitrogen with 3 oxygens. In each case, it's an anion. The NO2 has fewer oxygens, so it's nitrite. The NO3 has that 3rd oxygen, so it's 1 more, so it becomes nitrate. So the expectation is if you see NO2, you know that's nitrite, and if you see NO3, you know that's nitrate. Sulfate is similar, so that can be SO3, it can be SO4. The 3 oxygen one, because it's less than 4 oxygens, that ends in "ite," so it's sulfite. And then SO4 is sulfate because it has 1 more oxygen. So once again, if you're given SO3, the expectation would be that you would know that sulfite, and if it's SO4, you would know that it's sulfate. So there is a bit of pattern here. If you look at the groups, remember the groups were the columns, right? And then the periods are the rows across. We see that there are some things that patterns that we can pick up. So when we see these, so we have phosphate, sulfate, perchlorate in the period 3. And what we see is we go from right to left. So we have a phosphorus with 4 oxygens, a sulfur with 4 oxygens, a chlorine with 4 oxygens. But as we go right to left, so from 7A to 5A, we see that the charge increases as you go across there. So even though the number of oxygens stayed the same, the charge changed. If that charge changed, what is that telling us about the phosphorus, the sulfur, and the chlorine? How do we get that negative charge? If something has a negative charge, what did we say that means about that element or that ion? The only way we can get a negative charge is by picking up electrons, right? So that's telling us that we've got more electrons in the phosphate ion than we have the perchlorate. So as we go from right to left, we're picking up more electrons, even though the oxygen is the same amount. You see the same up on top with the carbonate and the nitrate. Going from right to left, we see that charge increasing. So it goes up from -1 to -2. The other thing we see is that in period 2, the most oxygen atoms that we're going to have attached to the other atom is 3. We get in period 3, and now suddenly we can have 4 oxygen atoms attached. This is another one of these periodicity things that we can observe. So the 2 things that we see on this is that period 2, the max is 3 oxygens. Period 3, the max is 4 oxygens. And in each of them, we see as we go right to left, the charge increases from -1, -2, -3 in period 3, -1 to -2 in period 2. When we talk about these oxyanions, it can get confusing. And the chlorine is, I think, a really good example of it, because you've got a lot of different things that you can have with chlorine with different amounts of oxygen. So the simple anion for chlorine, so in other words, just chlorine by itself, no oxygens attached, that's on top there, and that's chloride. Remember, we said if it was just the element and nothing else with it, it's whatever it is, ide, chloride, bromide, iodide, whichever one of those it might be. Then when we start adding oxygens to it. So here on the left, we have 4 oxygens. So it's per chlorate. The per means 4. And then we ended in 8. So it's perchlorate. We lose one of those oxygens, and now it's chlorate. We lose that per part because we don't no longer have 4 of those oxygens. We lose another oxygen to get ClO2, and it's chloride. And then finally, just the ClO is hypochlorite. So a bunch of them associated with chlorine. We've got 5 different things there. Once again, no oxygens with the chlorine, and it's chloride. We kind of start with 4, and it's perchlorate. We have 3 chlorate, 2 chlorite, and then finally hypochlorite for just 1 oxygen. So with each of those oxygens that we lose, the name changes a little bit. Once again, this is just something that you just memorized. Let's talk about acids for a little bit. If the anion of the acid ends in "ide," to have the acid name, you change the "ide" to "ic." So HCl, hydrochloric acid. Hydro plus chloride, we change the "ide" to "ic." HBr, hydrobromic acid. We have the hydro in front. We change the bromide to bromic. Hydroiodic acid. Once again, we have the hydro part. Iodide, change that to "ic." So for these simple inorganic acids, hydro, whatever it is, "ic." Hydrochloric, hydrobromic, hydrofluoric if it was fluorine, and on down the line. If the anion begins in "ite," we change it to "us." So we have our first one here, HClO. We learned up here that ClO is hypochlorite, right? That's the one on the far right. So that's hypochlorite. So we have chlorite. Ite becomes "us," hypochlorous acid. ClO2, chlorous acid. So once again, it ends in "ite," it becomes OUS. And then finally, anion, if it begins in 8, then it changes to "ic." So it can be a little confusing because up on top we had "ide," and that changed to "ic." Down here, we're saying 8 changes to "ic" as well. So HClO3, chloric acid, perchlorate becomes perchloric acid. So what we're seeing here is if it was sulfate, it would be sulfuric acid. That 8 changes to "ic." So hopefully what you're seeing here is that in order to name these acids correctly, you have to learn how to do the naming of the oxyanions or the anions in general. So as we kind of go through this, you see this kind of like a progression of stuff to learn. First, you had to learn that Cl is chloride. Then you would start learning some of the oxyanions. And then finally, you put that information together with some of these acid naming rules. So it's kind of like building on top of each thing. So you kind of learn the first thing first, and then you learn the next. All right. So let's talk about binary molecular compounds. So we use a prefix. When we have non-metal compounds, we use a prefix to tell us how many of those atoms are present. And so this table of prefixes here, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, you should know that. You should know that hexa means 6. You should know nona means 9, things like that, okay? Because these prefixes will be used in these naming of these compounds, but it'll be used in a host of other things as well. So, as I said, the prefix is used to tell you how many elements, how many of that element is there in the compound. The thing to remember, though, is for the first element, you don't use the 1, and you typically don't say mono. It's just assumed that the 1 is there. If you look at the periodic table, the element that's furthest to the left is usually written first, okay? So like if you had sodium chloride, you think of where sodium is, that's way over in that group 1 elements. So you write the sodium first and then the chlorine will be written next. The reason for that is you typically write it with the cation first and the anion second. And remember we talked about how the metals like to be cations. They like to donate electrons. The non-metals like to be anions. They like to pick up electrons. Because those metals like to donate electrons, if you lose an electron, you go from neutral to now you have positive charge. You've lost one of your negative charges. If you're the non-metal and you like to pick up charge, well, you pick up that electron from that metal, and now you have a negative charge. So that's just by convention how it's written. It's usually the further to the left is written first, and the right-hand side is written second. Let's talk about some binary compounds. So what is a binary compound? Can anyone tell me what that is, what that means? What it means is you have two different atoms in the compound. So you can have more than 2 atoms total, but there's only 2 types of elements in there. So here, carbon dioxide, we have 1 carbon and 2 oxygen. So we have three things there, 3 atoms there, but we only have 2 elements. Carbon tetrachloride, we have 5 atoms there, but we only have 2 elements. So that's what we're talking about when it's a binary compound. So when we name these, once again, this time we're going to end it in "ide" if it's a binary. So carbon, and then 2 oxygens. So we're going to change it to oxide. And because it's 2, it's di. Remember, we go back to our table here, and 2 was di. We see 4 is tetra, and sure enough, carbon tetrachloride. So we have carbon, 4 chlorine, so tetra, and then chloride. And then if the prefix ends with an A or an O, and the name of the next element begins with a vowel, you don't write 2 vowels in a row, is the easiest way to explain this rule. So let's look at the N2O5. So we have 2 nitrogens, and since it's not a 1, we're going to say dinitro. So dinitrogen, and then we have 5 oxygens. So that's penta, right? But penta ends in an A, oxide begins in an O. We don't want the 2 vowels, so we say pentoxide. Okay? If this isn't confusing you, nothing will. So that's why you really got to just spend some time looking at it. There's, I'll tell you, I've been doing this a long time. I still have to stop and think about a lot of this stuff because there's so many of these little rules. The last one we'll look at is carbon monoxide. Carbon, we don't have a mono there, as you said, we don't do the mono on that. Carbon monoxide, but there we do on the second, we do to indicate 1. It's just on that first one that we don't say mono. Once again, another rule that can confuse you. But here we do say carbon monoxide. Once again, we have the double vowel thing. So we don't have two vowels in a row. Okay, let's just talk briefly about some organic compounds. So organic chemistry is centered around working with compounds that contain carbon. And usually it's carbon, hydrogen, nitrogen, oxygen. Those are the kind of the main components of organic compounds. And as I said, there's a whole nother year-long chemistry class that just works on organic chemistry. And to be honest, when people think about chemistry, a lot of times, what they're really thinking about is organic chemistry, because organic chemistry is typically synthesis work. So in other words, you're mixing chemicals together and you're creating some new compound. And so we're not going to go into a lot of organic chemistry, but we're going to just talk about a little bit, just to give you a feel for some of the rules that they have in the organic chemistry world for nomenclature. The simplest organic chemistry compounds are what they call hydrocarbons. And these are compounds that contain only carbon and hydrogen. So hydrocarbons, hydrogen and carbon. And there's three examples: methane, ethane, propane. So all of you are going to use propane this week in the lab. Some of you have already. Propane is what we use in the Bunsen burners. So when you do the lab this week and use a Bunsen burner, propane, that one on the right, the 3-carbon one, that's what you're using in that, in the little fuel tank that was with it. It's also, propane is also, if you have a gas grill at home, that's what you're burning in, it is propane. These simple organic compounds where you have carbon and hydrogen only, and you have only single bonds, so in other words, just one line to each of those atoms, these are called alkanes. And the first part is based on the number of carbon atoms in the name. So once again, going back to that list of 1, 2, 3, 4 and all that, that's how we get methane, ethane, propane. So meth is 1, eth is 2, prop is 3, butane, butyl is 4, pentyl on down the line. And then we ended in ane. So methane, ethane, propane. If it was 4, it'd be butane. 5 would be pentane, hexane, on down the line. If we take one of those hydrogen atoms and replace it with a functional group is some combination of atoms that is common. In this case, the functional group would be an OH, an oxygen, with a hydrogen bonded to it. If we replace one of those hydrogens on these alkanes with an OH functional group, then that becomes an alcohol, is that class of compounds. So here we see methanol, ethanol, propanol. We have that same meth, eth, prop type thing that we had with the alkane to tell us how many carbon atoms are there. So 1, 2, or 3 carbon. Now, do you see the propanol? There's a 1 in front of the P. Does anyone know what that means or why we would have that there? What that tells us is that 1 tells us the location of the OH group. So it tells us that the OH group is on the first carbon atom. And so that OH could also be on the second carbon atom. If that was the case, then it would be 2-propanol. If you brought it over to the next carbon atom, would it be 3-propanol? It wouldn't. It would still be 1-propanol because those are the same molecule. It's just on the end. So we'll talk about this later, but those are considered isomers. So in other words, it's the same number of carbon, oxygen, hydrogen atoms in those two propanol molecules, but the arrangement is different. So when you name these, because it's got that OH group on there, it's going to end in OL. So that's the methanol, ethanol, propanol. So basically it's methane, but instead of methane, now it's methanol because it's an alcohol. Same with ethanol and propanol. Okay, this is what I was mentioning. If you have two or more molecules that have the same formula with different structures, then we call those isomers. So 1 propanol, 2 propanol have the same, but it's just that connection of where that alcohol group is. Is it on the first carbon or is it on the second carbon? So, a lot of things to memorize in this chapter. We have element names and associated symbols. We have nomenclature. We have a lot of naming rules associated with the nomenclature. We talked a little bit about some of the organic. All we talked about was alkanes and alcohols, so there's not too much there. The inorganic stuff, there's a lot more there. So what I would ask you to do is to go and you know, spend some time looking at the slides, spend some time looking at those tables, and start trying to get a feel for just some of the rules on naming and what some of the ways of naming the compounds are. Here are some problems you can take a look at and just see how well you do. So that ends chapter 2. As I said before, what I would like to do is, this is going to be it for today. What I'd like to do is give you some time between now and Monday to look at some of those homework problems and work on memorizing some of the rules for naming compounds and some of the tables for the prefixes as well. I can't stress enough how important that is to learn that stuff for both the tests coming up and then just down the line as the semester goes on. Then on Monday, what we'll do is I'm going to go back through chapter 1. We're going to kind of go quickly through 1 and go quickly through 2. And I'm going to go through those chapters and just highlight once again for you the things I think are really critical that you should be comfortable with, okay? And then on Wednesday of next week, we'll have our first full exam. So that'll be worth 100 points. It'll be more questions. There'll be more time, et cetera, et cetera. But really, also go back and take a look at the quiz to make sure you kind of understand how the problems on the quiz were done, understood how the thought process was on the questions that were, you know, were term questions and things like that. As you're going through this stuff, if you have a question or anything, please feel free to send me an email or something, or if you want to come and talk, you can set up an appointment, you can come by. Any questions from either anyone in the room or anyone on Zoom? Okay, we'll stop there then today, and I'll see you guys on Monday or Tuesday. Thanks.